What we will be discussing today is a continuation of what we were doing in the last class. So, in last class, we had discussed about Bose gas, and we saw that how we can use the expression for the mean occupation number, and then how we can use it to find the different thermodynamic variables. And from there, we could see that Bose gas show this typical behavior of condensation beyond a particular, below a certain temperature, which is called the critical temperature, and that state is called the Bose-Einstein condensate. And then there are certain conditions. So depending on the dimensions of your system and depending on how the dispersion relation is, uh, you can have the condensation or condensation might not form. So all these conditions we had discussed in the last class. So what we will do today is that first I'll recap the basic concepts of basic expressions of the different thermodynamic variables for the Bose gas. And then we will see what happens or how does the expressions change when we have harmonically trapped Bose gas. Under what conditions does the condensation start, or to frame it differently, what is the expression for the critical temperature and all of that. And then we will generalize it for a general Bose gas system depending on some dispersion relation. Okay, so that's how today's class would go. Second. Okay, so as usual, we will discuss the concepts. There'll be some problems that we will solve, and if you have any doubt, you can get back to me. So now, recap of what we had discussed in the last class. So this is for you to remember the basic things so that you don't get confused. So we know that if we recall our concepts of grand canonical and symbol, we know that this is how you can write the potential, the grand canonical potential, which can be written in terms of Q, where Q is the grand canonical partition function, and that has an expression like this. And for Bose gas, you put A equal to -1, and then this is the expression, right? So you can use this expression to find the pressure, or you can use it to find the equation of state. So now, similarly, you can get an expression for n, where n is the number of particles, and Ne here, this is called the mean occupation number, right? So in case of Fermi gas, you had a +1 here, and this is the expression for the Bose gas, right? And then what this tells you is that for this to be finite and defined, your z e to the power minus beta epsilon should be less than 1, which in a way tells you that mu, that is the chemical potential, should be less than epsilon, which implies that the chemical potential must be lower than the ground state energy. And so if you have free particles where there is zero momentum states, that's possible, and your energy is defined as p squared by 2m. So in that case, the minimum energy possible is 0. So there your u should be less than 0, right? And then if you use this relation, you know that z lies between 0 to 1. And for large V, where you can consider that the spectrum of single particles are continuous, you can move from summation to integration, and you would get something like this, right? You have changed the summation to an integration. And if you do that, what you see is, I won't go into the details because we had discussed it in the last class. But what's important is that once you do this, you can see that depends on the dispersion relation. So how energy depends on momentum comes into the picture here. And once you use the expression for the energy, you would get the exact expression for the pressure, right? And for Bose gas, A would be -1. So for non-relativistic free particles, you can consider energy to be given as p squared by 2m. And then from there, you can define a density of states. And you can see that in 3D, for free particles, the density of state goes as energy to the power half, right? But depending on which dimensions you are, suppose if you are in 2 dimension, you would see that you won't have any energy dependence. While in 1D, you will have an energy dependence of epsilon to the power -half. So depending on your dimensions, the density of states would change, right? And then what we saw is that you can use this relation, but this in a way tells you that in the density of states, they have not considered the density of states for the zeroth level, right? So we explicitly considered the case of epsilon equal to 0 here. And then similarly, we write the expression for pressure as well as the number of particles. And if you solve it further, what you would get is something like this, where you have defined this Bose-Einstein function, which is given by this integral here. This is actually a series which is given by this expression here, right? And then what we see that we can also write the internal energy in terms of the Bose-Einstein functions. And similarly, we can use this relation to even find the specific heats or the pressure. So another thing that's here is that, so if you look back into the expression for the number of particles, you see that n minus n naught by v is given by this expression here. So n naught is the number of particles in the zeroth state. So in a way, the numerator here is the number of particles in the excited state. So you can write Ne, where Ne is the number of particles in the excited state, as given by the expression here. Now, because G, that is the Bose-Einstein function, is bounded, that means Ne is bounded. So that sets a limit, or that sets the largest value of Ne that is possible, which is given by the case when Z is equal to 1. And if you do that, so when Z is equal to 1, we write the Bose-Einstein function by the zeta function. Okay. And then if you substitute it here, you would see that Ne has a upper bound given by this expression here. So as long as your number of particles are less than Ne, all particles will be distributed over the excited state. But then if n goes beyond Ne, so if n is larger than Ne, you will have any number of particles in the excited state, which is given by this expression here. But then whatever is left will go to the ground state, right? And this is the expression for Ne and n naught. So that means once your n goes greater than the maximum limit of Ne, there'll be particles that would gradually come to the ground state, and that is where the condensation starts. Okay. So now what happens here is that under this condition, when n is much greater than Ne, or n is greater than Ne, their Z tends towards 1. Okay. So for all value, so whenever the condensation starts, you can consider Z to be 1. So in those cases, you can replace the Bose-Einstein function by the zeta function. Okay. And so what it tells you is that the condition for the onset of Bose-Einstein condensation is given by this relation here, right? And so if you hold n and v constant, you can get an expression for the critical temperature, which is given by this expression here. But you need to be careful that this zeta function or this power, whatever you are seeing here, comes from the fact that you have used a free particle. So you have considered that the energy goes as p square by 2m, and you are doing it in 3D. So depending on your dispersion relation and depending on which dimensions you are, this factors change. So the expression, it's not a universal expression. The procedure of approaching to the expression is universal, but then this expression is not universal. Depending on your dimensions or the dispersion relation, the powers and the values would change, right? So this happens for free particles in 3D, free Bose gases in 3D. And what this tells you is that when temperature goes below the critical temperature, what happens? You get two phases. One is a normal phase consisting of any particles distributed over excited state, and you get a condensed phase consisting of n naught particles accumulated in the ground state, right? So that means if we plot, we'll see that below Tc, you will see that Ne by n goes as uh, this value, so it gradually goes down, while n naught by n, yeah, so n naught by n gradually goes down. So beyond Tc, n naught is 0, while 1, which is for Ne by n, you see that beyond or for temperatures greater than Tc, this is equal to 1, and below that, it gradually goes down to 0, right? So at T equal to 0, you would see that all the particles would come to the ground state. And you can find the corresponding expression for Z. So below Tc, Z is taken to be 1, and then it gradually decreases, right? So if you use that relation, you can say that below Tc, the pressure expression changes to something like this, where you have replaced the Bose-Einstein function by the zeta function, okay? And beyond Tc, you can, what you can do here is you can replace this lambda q by this G3 by 2Z. So then you get this expression for the pressure. So we had discussed all this in the last class. But now what we will do is we will try to, and this is the expression for the internal energy. Okay. And then similarly, you can find the specific heat below and above the critical temperature, right? And you can see that, so below the critical temperature, Cv goes as T to the power 3 by 2, and then it reaches a maximum, which is higher than the classical value. Okay. And then it gradually drops down, and it tends towards the classical limit as T tends to infinity. Okay. So now what we will discuss is we will discuss about the harmonically trapped Bose gas. Okay. So So what is different from the last case? So the last case was for for free particles, but now the Bose gases are trapped. Okay. So in 3D for free particles, we saw that the density of state goes as epsilon to the power half. But that's not the case for harmonically trapped Bose gas, right? Because now you have the Hamilton given by this expression here. So you can see that the energy terms would have a dependence. So it has extra energy. It is not just the free particle energy, but you have the energy levels which are discrete and which are defined by this relation here. So nx, ny, and nz are for the corresponding ex, ey, and ez. And then you have this 3 by 2, which is the zero, so zero field energy. So this is 3 by 2 h cut omega, right? So if you consider omega x, omega y, and omega z to be equal, then you would get this expression for energy. But now, given a particular energy, what are the number of states that can lie between 0 to epsilon? How to find that? So what we do here is that we do an integration. So over different values of Ez, Ey, and Ex. Okay. But then Ex plus Ey plus Ez should be equal to E. So accordingly, we have set the limits. Okay. So Ez goes from uh, epsilon, which is the total energy, minus Ex minus Ey. Similarly, then we do this integration, and then we put the limit of epsilon. It's going from epsilon minus epsilon x. Okay. And finally, Ex goes from 0 to epsilon. So this is to ensure that the sum of Ex plus Ey plus Ez goes to epsilon, which is the total energy. Now we want to see that, and this is for normalization, where we have used the corresponding so h cut omega for each uh, energy along each directions, x, y, and z. So we have h cube, and then we have omega naught cube, considering that omega x, omega y, and omega z all are equal to omega naught. Okay. And then once we do this integration, here you can see that we have integrated Ez, and then we have put the limit. We have similarly integrated E for dEy. Finally, when we solve it, we get something like this, right? And if we put the limits from 0 to epsilon for Ex, what do we get? We get this expression. So this gives you the total number of states that can lie from 0 to epsilon. Why we are doing this is because we want to find the density of states. As we had said previously, the density of states for a harmonically trapped gas would be different from what we had done in the last case for the free particles. So in order to find the density of states, what do? We first find the total number of states, okay? And then we differentiate with respect to energy. That would give you the number of states that lies between epsilon to epsilon plus d epsilon. And that is what is the density of states, right? So now you have got g of epsilon. So now if you find the density of states, you would get something like this, right? So what we will now do is we will use this expression for the density of states and substitute it in our integrals and find the corresponding expressions for the different thermodynamic parameters. Okay. So if you consider that ln q was given by something like this, where you had this summation, if you change to integration, considering that your the volume is very large, so in those cases, you can do the integration. So how do you shift from summation to integration? Is you do an integration over of this term, and then you have this density of states here, right? So if you substitute that, you would get an expression for ln q. So what we will first start with is we will start with an expression for n. Okay, so n, we know n is summation over all values of n that is possible over the mean occupation number. Okay, and this is what is the mean occupation number. If you change to integral, you would get something like this. Now, when you do the integration, what do? You substitute the value of g epsilon into the expression, right? And once you do that, now you have to solve. So what you do, you take x. So this is a variable transformation that you do. You consider x equal to beta epsilon. Okay. And then this is just substitutions. Finally, you get an integral like this. And now if you remember, this can be written in terms of the Bose-Einstein function that we had previously discussed, right? So this is the general expression for Bose-Einstein function. So if you use this relation, you would get n as something like this. So this is your expression for n. Okay. So now, again, the maximum value of n can be given by the fact that maximum value of g nu z happens when z is equal to 1. So putting z equal to 1, what do we get? We get, so then the g3 of z changes to zeta 3, right? And this is what we get. This is the maximum value of n that is possible. So beyond this critical value, condensation will start, right? So in a way, now if you replace T by Tc, this expression can give you the expression for the critical temperature. So for T greater than Tc, what would happen? Your Ne by N would be equal to 1. And there you can replace N by this expression, right? Here you have G3 of Z. But then once you go below Tc, there what happens is that particle starts to fill the ground state, right? And their N is greater than Ne. And then what happens is Ne by N goes as T by Tc whole cube. So if you think of the graph that we were discussing, beyond Tc, Ne by N is always 1, but then it gradually decreases, right? And the decrease follows this trend. Again, for T greater than Tc, N naught, that is the number of particles in the ground state, would be 0. And for T less than Tc, N naught will be 1 minus T by Tc whole cube. So that N naught plus Ne is equal to N. So that means this trend, this is how Ne by N goes, right? So 1, the plot that is shown by 1, that would follow this trend, T by Tc whole cube, right? And when you go down, it would follow. So this is for N naught by N. N naught by N gradually goes down as the temperature increases, and it follows the trend of 1 minus T by Tc whole cube, right? So if you recall, let me go back to this expression that we had initially discussed. So what will you see is that, look here, we had similar graph, right? But then here, the dependence was different. How can you understand that? So you can see that in this case, Ne by N went as T by Tc to the power 3 by 2, right? So in the free particle case, the exponent is 3 by 2. While in the case of harmonically trapped particle, we get an exponent of 3, right? So that is because now depending on your dispersion relation or depending on your Hamiltonian, your power or the dependence over temperature is different. So you need to be careful about these things, right? Okay. So now, okay. So now if you want to find the expression for energy, how do you do that? So you can find the expression like, so this is summation over En, and then you multiply each energy by their corresponding occupation number, right? So similarly, if you change to integration, you would get an expression like this, right? Then you put the expression for E, and now if you solve for it, you will get an expression like this. So this is just similar to what we had done for the case of N. But then by looking at it, can you tell me what would be the expression for the, so how can we replace this integral? What would be the value of the Bose-Einstein function from here? Any idea? Hello, are you guys following? So I'll consider that you are understanding. So what we are doing here is that now if you look back and look at the expression for the Bose-Einstein function, you would see that this integral can be replaced by G4 of Z, right? Because you have this, so the power was given as alpha minus 1. So if you correspondingly find the value of alpha here, it would be G4, right? So you get an expression for the internal energy. So this is your expression for the internal energy. And so now you can use this relation or this expression in order to find the different specific heat and other parameters. Okay. So now for T less than Tc, what can you do? You can replace Z by 1, and then your Bose-Einstein function is replaced by the zeta function, right? So here what you can see is this is a constant. Kb is a constant. So what you, and this Kb by h cut omega naught whole cube is also constant. So you see that your U goes as T to the power 4, right? So now if you want to find the expression for the specific heat, you do a differentiation, okay, with respect to, so this should be capital T. This is wrong. This should be capital T. So you're doing an integration with respect to, hmm, yeah. So then if you do that, what you see is that you get an expression where Cv goes as Tq, right? And then this is the exponent or the constant in front. So in a way, you can see that Cv by Nkb goes as 12 into zeta 4 by zeta 3 T by Tc whole cube. So this is how your Cv goes. If you remember, in the last case for the free particle, your Cv below Tc used to go as T by Tc to the power 3 by 2, right? And here it goes as T by Tc to the power 3. At Tc, what do you get? At Tc, you get Cv by Nkb that goes as, so you put Tc, T equal to Tc. So this term goes to 1. So this is your expression of the specific heat by Nkb at the critical temperature, right? And then beyond Tc, when T is greater than Tc, you can no longer replace Z by 1, right? So there, what happens? So you just have the same expression, but then you have G4 of Z. Okay, you can no longer replace it by the zeta function. So now this is your expression for U, and this is your expression for N. So if you look at it, you will see that you can replace this term by N by G3Z, right? And so this is your expression for the internal energy. So internal energy is given as 3 kBT N, where N is the number of particles. And then you have the ratio of these two Bose-Einstein functions, G4 of Z by G3 of Z. Okay. So now that was your expression for U. If you have to find the expression for the specific heat, how do you do that, right? So here, what do you do? For T greater than Tc, this is your expression. So you have to do a differentiation with respect to temperature, right? So this is your internal energy. You want to find specific heat. So you do a differentiation with respect to temperature. But now, what is the expression? This is the expression of internal energy, right? You put it here. So that means now individually, this is, so first you do a differentiation of the first term, where so ddt of T goes to 1. So you get the first term here. And in the second term, you do a differentiation where you have to individually do a differentiation with respect to temperature for each of these terms. So you have to find the expression of dg4 dt, dg3 dt, right? Only then you can solve for this expression. So we will now try to solve for this differentiations. So DGM for some value of, so consider that the dummy variable here is M. Okay, you can put it as 3 or 4 depending on whatever you have to solve. So this is the general case. So DGM dt is given as DGM dz into dz dt, right? And we know from the property of the Bose-Einstein functions that DGM dz is given as 1 by z g of n minus 1. Okay, so if you put this in this expression here, what do you get? You get dgm dt is given as 1 by z dz dt into g of m minus 1 z. So now if you put m equal to 4, you get dg4 dt is 1 by z dz dt g3 of z. Similarly, if you put m equal to 3, you get this expression. Okay, so each of the derivatives of one index of the Bose-Einstein function has a dependence over the of the Bose function of the previous indices. Okay, so what this tells you is that now if you want to find the expression for this differentials, you have to know the expression for 1 by z dz dt. This is still not known to you. So we want to find an expression for 1 by z dz dt. Okay. So how do we do that? So now remember that this is your expression for n. Okay. So you do a differentiation with respect to temperature. You do a differentiation of n, and then you take this to this side. Okay. So you do a differentiation of this term, and that is equal to ddt of g3z, right? If you do an differentiation of this term, you would get something like this. So this is not minus, this is like, it should have been something like, it's not minus, it's a product, and then you have this minus sign, right? So you are doing a differentiation of uh, 1 by t cube, right? So if you do that, what do you get? You can write from here that ddt of g3z is given as minus 3 by t of g3z. What you have done here is you have replaced this term from this expression here, right? So if you do that, now what you can do, you can use this expression in the last expression that we had written. We had written that ddt of g3z is equal to 1 by z dz dt of g2z, right? So what we will do, we will use this expression, in this expression here. So that's what we have written, right? And what we get from here, 1 by z dz dt is given as minus 3 by 2 g3 of z by g2 of z. Okay. So if you now use this expression of 1 by z dz dt, you can get an expression for ddt of g4z as well, right? So what is then done is that, remember that this was your expression for cv by nkb. We are finding these terms in order to find the expression for this term here, right? So what do we do? We put the terms here. So if you replace these terms, so you can take 1 by z dz dt common, and then you will get something like this, right? And then you finally replace the expression for 1 by z dz dt. And if you solve for this, you would get an expression like this. This is only for this part, okay? Only for this part. This part is already solved, so we just keep it there and we try to solve and simplify this part, and this is how it looks like. Correct? Okay. Let me erase this. Okay. And then what we do now for t greater than tc. So you remember, this is whatever we are solving for t greater than tc. Okay. And then this is your expression. Okay. Now what you have added is you have added the first term, which was already there. So if you look back, you already had this term and you found an expression for this term. So now you write both of this together. And what you get an expression for the specific heat. And this is your expression for specific heat, right? So in high temperature limit, you can put g of z as close to z, okay, tends towards z. So in that case, these terms will all go towards 1. So you can see that Cv by nkb goes towards 3. So it tends towards the classical limit, right? Now what happens at t equal to Tc? at t equal to Tc, you see that Cv by nkb is given by this relation here. What you have done here is you have replaced all the Bose-Einstein functions by the corresponding zeta functions, because at t equal to Tc, z is equal to 1. Okay. So if you do that, this is your expression for specific heat at T equal to Tc when we are approaching from Tc plus. What do you mean by this? Because see, initially we had started with the case for T greater than Tc. So we are tending towards T equal to Tc from the limit. We are tending towards the limit of T equal to Tc, but we are tending to from the direction of Tc plus. So we are tending from values of temperature greater than Tc. But now if you think back, the expression that we had got for the specific heat when we were trying to solve for the case of T less than Tc, there the expression at T equal to Tc was not equal to what we got here, right? So this does not match with the previous expression of Cv at T equal to Tc when approached from Tc minus, right? So what was that? If we look back, you would see that for T less than Tc, you got this expression for T equal to Tc when we had initially started from temperatures lower than Tc, right? Okay, so that means there is a discontinuity in specific heat. At T equal to Tc, when we are approaching from Tc plus, you get this expression. But when you approach from Tc minus, you get this expression. Okay, so that means there is a discontinuity, and the discontinuity is given by this expression here, right? So if you look at the expression for Z, Z remains 1 for values of temperature lower than Tc, and then it gradually falls. Okay. And this is how your energy looks like. But these are, so you can see that there is this kink here, right? So what happens now when you find the specific heat, you see that there is this discontinuity, right? So this is your value when you come from Tc minus, it tends towards this value, while when you come from Tc plus, it tends towards this value. So there is a discontinuity, right? Okay. So now, depending on what we discussed till now, can you try to solve for this question? So initially, the only difference here is that in the last example or the last discussion that we were doing, we were solving for three-dimensional trap. But now you have n bosons in two-dimensional trap. So can you first tell me what the density of states of the system be? So try to solve it. I'll give you some time. Try to solve for the density of states for the case when you have two-dimensional trap. N bosons in two-dimensional trap. Is the question clear? If you guys have any doubt in how to proceed with the question, you can ask.
Ma'am, the Bose-Einstein condensate for two-dimensional trap would be possible only if the temperature goes down to zero, right?
So how do you define that? Why do you define it like this? Like
No, I learned that in quantum mechanics.
no. So first try to find the general expression. So if there is some limit like that, we will get it from the expression as well, like generally, right? Try to find the expression. So depending on whatever discussions we had till now, so follow the same procedure, But now do it for two-dimensional trap. You would get some expression for the critical temperature, and then we'll see whether that's true or not. So if I go back, maybe I'll show you where we started, right? And then you can proceed for the two-dimensional case. So for three dimension, this is how we had defined the density of states, right? Now, what will happen when you have a two-dimensional case? Try to look at this and then try to solve for the two-dimensional case. Can you tell me how you are thinking of proceeding with the question? And then I can help you in understanding whether you are proceeding in the correct way or not.
We only take omega x and omega y,
Okay.
and because it is a two-dimensional.
Right. So you'll have two integrations, right?
I was thinking, yes.
Okay.
Ma'am, the h cross would be squared or it would still remain cubed.
So think what should be the case. Why are you getting this H cross omega terms here? So why are you getting three? You're getting three because you have this. So each of this EX, EY, and EZ has this n plus half H cut omega term, right? So that's how you get this three factors, right? So if you have two, then it should be H cut square by omega into omega X, omega Y, right?
Yes. Ma'am, and we would take the epsilon y as epsilon minus epsilon x, right?
The limit, right? 0 to epsilon minus epsilon X. So this limit consideration comes from Ex plus Ey should be equal to the total energy E, right? So
Hmm.
the first limit of Ey should go from 0 to epsilon minus Ex, And if the energy, the Ex limit should go from 0 to epsilon, right?
No, I was talking about the second integration, the d epsilon y.
Right. So that
For
should
that,
go from,
we would take it as epsilon minus epsilon x d epsilon x.
uh, no, why will you do that? See, you first you have to set a limit for, so the condition that you have to satisfy is epsilon x plus y should be equal to epsilon, right? Epsilon x plus just writing. Okay, so epsilon x plus epsilon y should be equal to epsilon. This is what we know. Now, first you are setting a limit for epsilon y, right? So
Yeah.
there the limit will be from epsilon minus epsilon x. Then you have dey. You do an integration over dey. Once that is done, the limit for dex will be from 0 to epsilon, right? So that you have all values of energy from 0 to epsilon possible. Is that clear? Like you first set the limit. So for some value of Ex, what would be the value of Y? The value of Y will be epsilon minus epsilon X, right? And then what are the possible values of epsilon that is possible? The possible values of epsilon X goes from 0 to epsilon. So that means the limit for Dex will be from 0 to epsilon minus epsilon X. And the limit for Ex would be from 0 to epsilon. Is this clear?
Yes, ma'am.
The same thing that we did here. So what did we do here? We thought that the sum of all three should be equal to epsilon. So what are the possible values of epsilon z given some value of Ex and Ey? So this is how the value should vary, right? And then once that is solved, so once you solve for the possible values of Ez given some value of x and y, what is now the possible values of Ey? That is limited by this relation here, right? So this is the limit 0 to epsilon minus epsilon x. And then what is the limit over Ex? The limit over Ex goes from 0 to epsilon. So in this way, you consider that all the cases for which you have energy ranging from 0 to epsilon.
Yes, ma'am. Now I understood about the limits. I was confused for a moment about the coefficient that we would take for d epsilon y.
The coefficient will be 1 by h cut omega y, right? So,
Yeah.
and for omega epsilon x, it will be 1 by h cut omega x, right?
Right, and then when we would integrate, it would be directly 1 upon h square omega x omega y into epsilon minus 0 into epsilon minus epsilon x minus 0.
Uh, wait, so
Put when we put the limits.
when you put the limits, and then so you have to put this limit also, right?
Uh,
Limit of epsilon x goes from 0 to epsilon.
yeah, so that would be epsilon minus 0.
So what would be what is the final expression then? So anything minus 0, that term is 0. So what is that? What is the non-zero term that you are getting?
Ma'am,
Yes, tell me.
ma'am, I get for the density of states, I get epsilon by h cross omega square. Is it right?
Yes, that's what you are supposed to get. So in the expression for G epsilon, this capital G epsilon, you will get an epsilon square.
Yes, ma'am.
So for Anushka, what I was telling is that uh, so it's correct, okay, Kamalesh. But then
Okay.
so here what you see is you'll put a limit from 0 to some non-zero value, right? The 0 limit will go away because that's 0. Consider see what you get for the non-zero part, right? So maybe I'll share the, then you can follow and check where you were stuck. Right. So your energy goes as something like this. So now you have a you have defined the total number of states by an expression like this, right? So when you integrate over dEy, what do you get? You get epsilon minus Ex minus 0. So minus 0 is 0, right? So you just keep this term, epsilon minus Ex, and then you do an integration over Ex, right? And the limit goes from 0 to epsilon. So now what do you get? This is on integrating, you get this term, then you put epsilon and you put 0. So 0 means all those terms would be 0. So what you get is epsilon square minus epsilon square by 2, right? And this is your expression for the for capital G of epsilon. Anushka, is it clear where you got stuck?
Yes, ma'am.
Right. So now if this is your expression for capital G, what is your density of states? You have to do a differentiation with respect to energy, right? So if you do that, what will you get? You will get epsilon by h cut omega naught square whole square. Correct? Clear? Clear, right?
Ma'am, I have doubt.
Yes, yes, tell me.
Ma'am, for the density of state, we get epsilon by h cross omega square.
Hmm.
So the dimension would be 1 over energy. Is it
The,
correct
di-
or
the dimension will be dimension of density of states.
is 1 over energy?
Okay.
Is it correct or density of state? It's
Yes, right, right.
oh,
It's
oh,
correct
okay.
because then you will multiply by some dE, right?
Yes, ma'am.
So now, so if that is your expression for density of states, what would be your, so how to address this question? Can a Bose-Einstein condensate form in this trap or not? So how can you answer this question? How will you plan to proceed? You have found the density of states, right? But if you are asked this question, how do you plan to proceed? So whether Bose-Einstein condensate form or not form will be answered by the case that whether you have a well-defined expression for the critical temperature, or whether given some condition for the Bose-Einstein condensation, whether the number like capital N, number of particles, whether that expression is defined or not. If it diverges, then the Bose-Einstein condensation cannot form, right? So that means what you can do is you can try to find the expression for N. Now, given GE, given your expression for the density of states, can you try to find the expression for capital N? So how to do that? Let us go back and check how we did for the three-dimensional case, and then we can follow the same procedure for the 2D case, right? So what we did this integration, right? So try to do this integration and see what is the, so what would be the value of the Bose-Einstein function for this case, for the two-dimensional case. So here they have replaced it by the case for the 3D. For your case, G epsilon will be replaced by epsilon by h cut omega naught whole square, right? So why we are trying to find the expression for n? Because once we get an expression for n, we can put this limit and then we can find an expression for the critical temperature, and we can see that whether that's well defined or not, well, whether under the condition when the temperature is equal to Tc, whether the number of particles is defined or not, whether that expression diverges or it's well defined, and that in a way will tell us whether we can have condensate formation or not, right? So that's why we want to find the expression for n. So one another thing to add here is that, see, here you have this h cut omega naught whole cube term, considering that omega x, omega y, omega z, all of them are equal. Okay. But if it was not equal, like you can find, I think, one such question in your assignment also, I was just going through. So there what happens? You have three different frequencies, maybe. So there you cannot replace it by omega naught whole cube. There you have to write omega x, omega y, omega z, right? So in the expression for n, or in all the expressions for the different thermodynamic parameters, you cannot write it as omega naught whole cube. You have to write it as h cut cube omega x, omega y, omega z if it is in 3D. Okay. Just I wanted to add this thing. So now you can proceed with this calculation. So how will this term first change? This is for 3D. Now, if it is for 2D, what will happen to this term? How will the exponents change? And how will the power of energy change in this integral? What would happen?
Ma'am, the power of x is 1.
The power of x is 1. Okay.
So,
So if the power of x is 1, what would be the value of nu here? If you look at the expression for nu, what would be the value of nu?
ma'am, you would be 2.
So that means here in place of 3, you will have 2, right?
Yes, ma'am.
And how would the exponents change? The constants in front change?
Ma'am, in front I get kpt divided by h cross omega naught whole square.
Right. So that's correct. So that's your expression for n. For others, it's clear. Anushka,
Yes.
Viram. Okay. So now once you get the expression for n, can you try to find the expression for the critical temperature? So how will you do that? You have to find the maximum value of n that is possible. And how can you get that? By putting z equal to 1, right? So if you put z equal to 1, G3 of z can be replaced by zeta 3. Like for your case, now it will be replaced by zeta 2, right? So then what would be the expression for n max? So for Nmax, now this, the factor in front is kBt by h cut omega naught whole square. And then you have, in place of zeta 3 that we had for 3 dimension, here you will have zeta 2, right? And then what would be your expression for Tc? So what you would do, you use this relation and then you can write Tc in terms of n and omega naught and zeta function, right?
Yes, ma'am.
Yeah, try writing. Maybe I'll go back to the question. Are you getting this expression? So what we have done here is we have replaced zeta 2 by its numerical value. So this is its numerical value. You can keep it as it is as well. But so what you see from here is that now you have a well-defined expression for Tc, right? And that is not equal to 0. So that has a finite value, right? So depending on your number of particles and depending on the frequency of so the normal frequency of the system, which is defined by omega naught here, you can have a well-defined critical temperature, right?
Okay, ma'am.
Anushka, is it clear?
Yes, ma'am.
Right. So now that means we found the expression for the critical temperature as a function of frequencies and like the trapping frequency and n, right? Now the next part of the question is that how much larger must the frequency in the third direction be for the system to display two-dimensional behavior? What what does this part of the question mean is that now you have said that you have a two-dimensional trap, right? So that means what it means physically is that the energy level spacings in the z direction is much larger than the energy that your system has in the 2D, right? So the energy in 2D can be defined by kBTC, right? While you are in the critical temperature. So you can define the energies, so the you can say the magnitude would go as kBTC, right? But then the first excited state or the first excited state in the z direction should be way higher than this energy so that the particles are not allowed to go in the z direction and they remain in the two-dimensional track, right? So in a way that means what this part of the question is telling you. Okay, so this is just to show that, so there in the 3 dimension case you had ne by n would go as t by tc whole cube, right? But here it goes as t square, and then n naught by n goes as 1 minus t by tc whole square. So depending on your dimensions, this expressions would change. Okay, so now the question that I was talking about, so for it to be confined in the 2 dimension, or for us to consider that it's in 2 dimension, the energy level or the excited state in the z direction should be way higher than the energy that the particles have, right? So that means h cut omega z should be much larger than kbtc, right? So now if you look at the expression for kbtc, it goes as h cut omega naught into root over n, and you have some constants, right? So that means this sets the limit or the condition under which you can consider that the particles are in two-dimensional trap, right? So when omega z is much, much greater than omega naught by root over n, you can say that the frequency in the third dimension is way larger for the system to go to the z direction or go to the energy states in the z direction, and it displays a two-dimensional behavior, right? Okay. So this is to show that whatever we had discussed in the three dimension, and then we followed the same kind of procedure in the two dimension, and we got some expression for the critical temperature. We saw that yes, condensation is possible under some finite, so below some finite critical temperature, right? So that's how we have to solve for any system given some dispersion relation, or some Hamiltonian. This is how we are supposed to proceed. So now if you do a general treatment of Bose gas, we can consider that the density of states GE goes as some general expression which is given as C alpha epsilon to the power alpha minus 1, right? Okay, so that means now if you consider free non-relativistic particles, like free particles, non-relativistic in 3D, you know that this is your expression, this is the expression, this is what we get by writing. You wrote it as 4 pi p squared dp, then you had changed from the momentum space to the energy variables, and you had finally got this expression in front, right? So that is your C alpha for free non-relativistic gas in 3D. And there you can see that your epsilon in that the alpha in that case, so you have uh, epsilon to the power half, right? So that means alpha should be 3 by 2, right? 3 by 2 minus 1 is equal to half. And then what happens when you have 3D harmonic trap? We see that so C alpha in that case would be given by this expression here. And there you would have GE, which is given as alpha minus 1. So here alpha is 3. So then it goes as epsilon square, right? So this is so now what we are trying to do is we are trying to find a general expression where general expression for a given density of states, right? So we follow the same procedure. We start with the number of particles and then we do this substitution. Okay. So what we do here is again, we change from the energy coordinate to some variable x equal to beta epsilon, right? And this is your expression that you get for the number of particles, right? So at high temperature, what you see at high temperature, you can replace G alpha of Z by Z, and that will give you an expression for Z, right? And so you can later use this expression for Z in order to find the complete series representation of energy or the specific heats. Okay. So what happens when temperature is less than Tc, you can consider Z to be 1, okay, and you replace G alpha by zeta of alpha, okay, and this is your value of n in that case. So this in a way will give you the condition for the condensation to form, right? You can replace beta by T, 1 by Kt, and replace T by Tc, and that will give you an expression for the critical temperature, right? So from here, you can finally get an expression for the critical temperature. So if you try to match with whatever we had done in the last class or this class, you will see that given the value of your density of states, this expression would match, right? And then similarly, we can solve for energy and you would get this expression for the energy. So what we can now do is we saw so in the last, this was your expression for Z, right? So if you use this expression for Z, and write the entire series for G alpha, okay? And then what you would finally get is this series which has all these zeta terms and Tc by T to the power alpha terms. And this will give you the total expression for the energy, okay? And then for T much, much greater than Tc, which is actually the classical limit, you get back the classical result, right? So for alpha equal to 3, you get energy equal to 3 nkBT, where for alpha equal to 3 by 2, which is for a free particle in 3D, you get 3 by 2 nkBT, right? So depending on your system, you can just put the values of alpha depending on the dispersion relation or the density of states, and you can find the corresponding expressions. And then from the energy expression, if you solve for the specific heat, which is done by doing a differentiation of each of the terms, and there what you will finally get is an expression like this, right? So what this tells you is that because of the summation sign, this tells you that as the temperature uh, goes much greater than Tc, you would again go back to the classical limit, which is equal to alpha n kb. But then how will you tend towards the classical limit? You will tend towards the classical limit from a value which is above the classical value, right? So you, if suppose if you have some plot, okay, and then this is your some, maybe consider that this is your classical limit, or the classically limiting value. This should be a straight line. So it limits to the classical value, but then it limits from a value which is higher than the classical value, okay? And this is what we had seen in the last case. We had seen that it was greater than the classical value, it reaches a maximum and then it comes down, right? That's what we saw for the free particles, and that comes from the fact that we have this plus sign here, so it's larger than the classical value, okay? So this was to generalize all that we had solved for the different systems, and you can use this general formula to find the expression of energy or specific heat or pressure and all these terms, right? So if you have to find pressure, you can use the relation of PV by KT. You know the expression for PV by KT, right? It is minus ln1 minus, so it come, I just forgot the complete expression. So it comes from the expression of the, it comes from ln capital Q, right? And so from there, you can find the expression for pressure and all the other terms, right? So now so that was about the general treatment of Bose gas. Now it's just to revise what we were doing. And now here we have to show that for ideal Bose gas, we have to show that we get this relation. And then once we get this, we have to show that gamma is equal to Cp by Cv, which is given by this expression here. So the thing is that how to show this expression, right? So to start with this expression. So this is what I was talking about. This is your expression for P by KT, where P is the pressure, right? And so we had seen that for ideal Bose gas free particles in 3D, this is the expression for pressure, right? Pressure by KT, right? So if you start with this, how can you find an expression for 1 by z dz dt? So what you can do is that you can consider pressure to be equal to some constant into t to the power 5 by 2, right? Why 5 by 2? Because you had this t here, and then you have lambda cube. So lambda cube means it goes as t to the power 3 by 2, and you have this another t here. So in that way, you get t to the power 5 by 2, and you have g 5 by 2 z, okay? So what you have to do here is that you have to do a differentiation with respect to t at constant pressure. So then this term goes to 0. And so you have taken this t already to this side, right? So this term goes to 0. And now you do a differentiation with respect to temperature, right? And this is what you get. So here you get an expression for dz dt at constant pressure, right? And this is the final expression for dz dt p, and this is given by this term here. But then how do you go from this term to this term here? You have to show that this is equal to this. What you got is something like this, right? So what relation do you have to use? Any clue?
Ma'am, so that the denominator must be del g 5 by 2 over del z is equal to g 3 by 2.
You also have this z here, right? Which is not present here.
Yes, ma'am.
So Yes. So if you remember, we had this relation dgm dz is equal to 1 by z g of m minus 1 z. That means now if you write dg 5 by 2 dz, it will be given as 1 by z g of 3 by 2 z, right?
Okay.
And if you use that relation, you would directly get from this expression, you would get to this expression, correct?
Yes, ma'am.
So that gives you an expression for 1 by z del z del t at constant pressure, right?
Okay.
Okay. So the first part of the question is then done. Now what you have to find is you have to find an expression for del z del t at constant volume, right? So how to proceed with this question? Any idea? So if we look back, we did a similar kind of thing. So what we did is that let me show you this part, then I think you can recall. So when we were finding the expression for this this different differentials like dg4 dt or g3 dt, what did we do? We tried to find an expression for 1 by z dz dt. And we started with the expression for the number of particles, right? And then we had seen that from here, we got an expression for ddt of g3z. And then we had substituted it in this expression to find an expression for 1 by z dz dt, right? And this we were doing at constant volume. And from here, we could get an expression for the specific heat at constant volume as well. So we have to follow a similar procedure. But now you have to remember that what we were solving in the question is for free particles. And here what is being solved is for the harmonically trapped Bose gas. So that means what will be different is this constant in front would be different. This value of, so it won't be 3, right? So these things would be different, but the process would be same. So you have to use the expression for n and then find the expression of 1 by z dz dt at constant volume, right? So try to write the expression for n for free particles in 3D, okay? And then use this relation, use this procedure. So if we go back and look at the general expression also, you would get an expression for n, right? We did a general treatment of Bose gas, right? So you can, okay, what? So this was your general expression. So now for free particles in 3D, what would be your alpha? Your alpha would be 3 by 2, right? So if you put that value here, what would be your expression for n? So this much we had done. Now we want to show this. So first of all, why we are getting to this expression is that we know Cp is given by, so it's like du dt at constant pressure. And then you write it as T ds dt at constant pressure. And then you can also write it as ds dz into dz dt. Similarly, here you have written at ds dn at constant n into dz dt at constant volume, right? And this is at constant pressure. So now if you do Cp by Cv, you would get this term, right? And then how do you solve that? So this is something we had got from the last problem we just solved, right? And we now want to find the expression for dz dt at constant volume. So how we do that? So the expression is this. How do we get to this term? Is that so you have to start with one second. So you have to start with the expression for n, right? So the expression for n would have a 5 by 2 term, right? Or not 5 by 2, one second. So the expression of n would have a term of 3 by 2z, right? And then you have to take all this term like n beta to the power alpha by c alpha gamma of alpha, that is equal to g of 3 by 2z, right? Alpha is equal to 3 by 2. And then you do a derivative with respect to temperature on both sides, right? And if you do that, you would finally get an expression of 1 by z dz dt, right? At constant volume. Am I clear how we are proceeding with that, with the question? So the same thing that we did for the three-dimensional harmonic trap case, same thing we will do, but the value of alpha is different. There the value of alpha is 3, was 3. Here the value of alpha will be 3 by 2. So you get an expression for n. You take all these coefficients on this side, and then you do a derivative with respect to temperature. So that means on the right hand side, you would get an expression of ddt of g 3 by 2z. And on the right hand side, you will have explicitly the value of, so 1 by, so this beta is 1 by kBT. So you have the temperature there. You do the derivative. You would see that some terms would be common, and that will again give you back g of 3 by 2 z, right? And so by that, you'll get a relation between dz dt. You get an expression for dz dt. Then you use that relation, okay, to finally get to this expression for 1 by z dz dt at constant volume. Is this clear? So there you will again use, so you have this g of half term that's coming because of this relation. You will be using this relation. So you'll have this g of half there as well. Are you guys stuck somewhere or is the process clear? So maybe I'll just once final time show this expression. I think then it might. So what did you get here? So you got something like G 3 by 2 Z by G2 of Z. So what you are getting here there is G of 3 by 2 Z by G of half Z. So you can see that there's this difference of 1 that is coming because you have to use this relation, right? And then you have to put this expression for, so this thing, once you take all the coefficients to the left hand side and do the differentiation, you would get some term, right? And then that would give you this expression. There you would have minus 3 by 2t term that comes in. And then you have to use this relation, and that would finally give you the expression. So you would get minus 3 by 2t d 3 by g of 3 by 2z by g of half z. So it's similar to what is being done here. Only now the expression for n is slightly different, and this it's no longer 3, it's 3 by 2. Okay. So if you do that, what you will finally get is the expression for 1 by z dz dt at constant volume. Okay. What is this? Okay. So you would get this expression for 1 by z dz dt at constant volume. And if you solve for, if you put these values in the expression for gamma, you would get to this expression for Cp by Cv. And that matches with what you have to be, what you had to show, right? And what this tells you is that when T is much, much greater than Tc, which implies that Z is much, much less than 1, so you're in the classical limit. So we can get the classical result of gamma equal to 5 by 3, right? And as T tends to Tc, Z tends to 1, and then you can see that G of half Z diverges, okay, as alpha to the power minus half. And so, so this in a way tells you that when in the expression for N or in the expression for pressure, if you have G of half, then it's it diverges, right? So if you go back and look at the expression for N, it's important and instructive because that would tell you something. So when you have G of half, suppose if you are in one dimension, okay, so what happens there? Your epsilon, one dimension free particle, free Bose gas in one dimension. So your density of states goes as epsilon to the power minus half, right? That means in that case, your alpha is equal to half, right? So that means in the expression for N, you would get G of half Z. And we just saw that G of half diverges, right? So if G of half diverges, that means in that case, N diverges. So that in a way tells you that in thermodynamic limit, you cannot have Bose condensation in 1D, right? Clear?
Yes, ma'am. It is clear.
Okay. So that was all for this class. Do you have any doubt regarding any particular part of this class or anything regarding to Bose gas, something like that?
Ma'am, which books would you suggest the textbooks? Because the different books are using slightly different notations.
Okay, so for what we had read or what I want to suggest would be Patria. Patria seemed to be quite uh, good in like with regard to me. So you can follow Patria. So these things are from some questions are also from Patria, and then I was following the instructor's lectures as well. But then Patria is quite inclusive; it covers all the sections quite well. So in Patria, you would also get an chapter for general, like for any dispersion relation or for any dimensions, how would the formulas or how for or the expressions for different thermodynamic parameters look like. So you would also get all those things there. There are, I think there's one specific chapter for this uh, general treatment of Bose gas or something. in some general dimensions or for some general dispersion relation. But then you also have an initial chapter on ideal Bose gas, and that mostly covers what's generally taught in this kind of introductory courses.
Okay, ma'am, can you please tell the complete name of the book?
Uh, okay, so the name of the book will be Statistical Mechanics, R.K. Patria and Paul D. Biel, something like this. This is how it looks. This is a very standard book for statistical mechanics. Statistical Mechanics, R.K. Patria.
Okay, ma'am.
Ma'am,
Ma'am, and the exam, the NPTEL exam, which they conduct for this course, uh, they said that it is going to be on paper. So does that mean they are going to ask these big derivations and things like that?
Actually, I have no clue regarding this because so this entire TA-ship or this classes that we are doing is with regard to some PMRF requirements, okay, TA requirements. So we were told that you have this is your so we have uh, we have to we generally go through what is to be taught in this week and then we plan our lectures accordingly. But I actually don't have any idea about how the course exams or the assignment evaluation and all of this is going on. So I can't help you in this regard. You can directly maybe mail the instructor or ask them because he might reply and he might know because he will know, I guess. Because I don't have any idea about how the course logistics are going. It's just we are here to just do some TA sessions in order to clear your doubts and discuss certain concepts. So I literally don't know how the exam will be.
Okay, ma'am.
Yeah.
ma'am, can you suggest any statistical books for competitive exams like CSIR Net and GATE? Is it Patria book is enough or
Patria is so what I would suggest is that for conceptual purpose, you need to follow some textbook. So only problem solving won't because you can solve endless questions, right? But it's important that you have the concepts clear first. So you can like in the first sections, there's another book for by Grainer. So you can search Grainer. So there are certain questions for those different ensemble problems like canonical ensemble, grand canonical ensemble, microcanonical ensemble. So I found that book quite good for all those kind of questions. Patra is a very standard book and you should follow it. So there should be at least one textbook. So you can consider Patria or Grainer or anything that you like. Choose one textbook, do that, and then you can solve questions like so. I think you have seen number of questions which I had copied from physics. There is this website. So they have this question banks. So you can try to follow. Uh, and then I think there are different groups. So what I would suggest is if you go through internet, you'll find different problem sets, okay, question papers and sets. So the, or Ari Hunt and all this, I think publishers, they have lots of question banks. What's important is go through the previous year questions. That's very important. Go through all the previous year questions, like at least 5 6 years. That's must. And then go through one two textbook, like one textbook, like thoroughly. That would clear your concepts. So I think that would suffice because only problem solving you can go on solving and have multiple tricks and ideas of solving questions, but then when you will have all the subjects together, it would be difficult to remember tricks. It's better to go by concepts. So, so I would suggest one textbook and then at least 5 to 6 years of previous year questions, and then you can solve as many like multiple choice questions from different question banks. Physics is a very popular one, I guess.
yes, ma'am? Ma'am, but Patria book is somewhat the excess questions are somewhat beyond the
No,
level.
you don't need to solve all the textbook questions, but go to the text. Like this
Yes,
concepts, what we are doing, no, you don't have to solve all the detailed questions because some of them are very involved. So,
yes,
so you don't have to do that, but you can choose some questions which you think would be
easy.
feasible to solve. But it's
Yes,
important to go to the theory, like the theory parts, like this concepts. Like, so see this, like for Bose gas, what might be important is that given some value of dimension, given some value, some dispersion relation, when is your Bose condensation possible, when it is not possible, or what would be the dependence of how would the critical temperature depend on the number density, what is the exponent, and how will it change for different dispersion relations. Okay, and so these things are standard questions. So like this question that we are doing, this might not come in your competitive exam, but what you can get is like suppose this relation, so this thing can come. So you can, maybe you have to use this concept that what happens in the thermodynamic limit, what would be the energy for some random dispersion relation and for some random dimension of your system, right? And so something like this. So here you can get an expression. So if you remember this, or if you know how to solve for this, you can tell how the specific heat, how the critical temperature depend on n, right? So you could have, you can have a multiple choice which has such kind of questions, right? So something like that. So you have to know how to solve the general cases. That's why I'm telling, if you go through Pachi or any uh, such kind of textbooks, you'll get the general treatment as well, and that's important to solve for you to be able to solve numericals faster as well. So if you remember in the last class, we did this condition that d by s should be greater than 1 for some given dimensions and for given dispersion relation where energy goes as p to the power s, right? So now if you are asked, suppose if some in some questions, if you remember that d by s should be greater than 1, you can tell that for for photons, you cannot have uh, Bose condensation in 1D, something like that, right? So that's how these things would be helpful. So try to solve it at least for one and once. Try to solve it so that you remember how to solve, and then remember the main results. That would be sufficient.
okay, ma'am.
Yeah. Okay.
Ma'am, can you give any advice on how to crack these exams? Do we really need tricks or go by concepts?
So you need a balance of both. See, you cannot. What happens is if you have too much of tricks to remember, you might miss on the concepts, and sometimes you might forget the tricks. So you should know what my suggestion would be, you to remember the basic concept, like the basic thing that how the, so for this question, how the mean occupation number looks like for Bose gas, Fermi gas, and um, Maxwell Boltzmann. Why do we have to consider the 1 by n factorial? Why not in for indistinguishable particles? These basic concepts, so that in case you forget, so if you know the basic concepts that your mean occupation number is something like this for Bose gas, okay, and you know that if you have to do an integration, you have to do it like g epsilon. So if the density of stress is this is how you find n. For energy, you have to have an energy term here, like energy into GEDE. So in case
Yes,
you
ma'am.
forget, so that you can find the expression. But then once
We
you
can
start
derive.
solve, so that in case
Yes,
you forget, you can derive. But then once you start practicing, some things you will automatically remember. So as you start solving, you will remember that. So suppose now you know that in 3D, the density of state goes as epsilon to the power half, right? You already know that. You don't have to solve for it. So similarly, when you try solving, you'll some results will automatically be stored in your brain. But then you should be possible, because you won't have questions only from StatMech, right? You will have from different sections, different subjects. So just remembering too many formulas would be very difficult. So you have to have some basic concepts in your brain, and then so that in case if you need, you can derive. Okay.
okay, ma'am. Yes, ma'am. Thank you, ma'am.
Okay. Okay. So I think that's it. We'll have another class next Monday. So while I think there I'll try to discuss and do a revision of whatever we had done in this session, like in this all those classes, and I think that would be the last class. So that's it. Okay. So if no more doubts, then uh, thank you. Okay.
Thank you.
Yeah. Okay. Bye.
Thank you, ma'am.